9. Hello everyone, welcome to Chapter 9. Not sure I got that on the first try. In Chapter 9 what we're going to do is we are going to look at radioactivity, and we're going to start out looking at natural levels of radioactivity and proceed all the way through the different types, and we're going to end up with medical and then finally nuclear power. So a lot of different aspects to radioactivity. First, of course, we're going to define a few things. A radioactive isotope, or a radioisotope, you hear people say sometimes, is an unstable atom. Okay, it has an unstable nucleus, and so what it does is it emits radiation so that it can become more stable. By doing that, though, it actually changes the nucleus. We've looked at things where, you know, our number of neutrons and protons were in the nucleus. We could change the neutrons, but these protons always stayed the same. Well, we're going to see in radioactivity that everything can change. There are no hard and fast rules here. The one thing that, well, I should say this, there is one rule that'll change. That is, if you change the number of protons, then you're going to change what element it is, okay, because that element still will have the same number of protons. Let's look at some of these as an example, and I'll show you what I'm talking about. There are stable forms of some isotopes, and there are not stable forms of others. Magnesium, for example, has a stable isotope, and it's called magnesium-24. A radioactive form of magnesium can be either magnesium-23 or magnesium-27. Notice that what I'm doing here is I'm writing that mass number at the top with the number of protons, the atomic number on the bottom with the symbol. And so magnesium-24 I write like that. In magnesium-27, which I write like this, what's the only difference? Those mass numbers, okay? So since the mass number is different, then, but the protons are the same, it's still magnesium, it just has a different number of neutrons, or it could, in the case of radioactivity, as we're going to see, have a different number of protons. Iodine has a stable form, iodine-127, which is used in a lot of medical applications, along with 131, which is the actual medical that you'll see used. It can also be iodine-125. Notice it can be less or it can be more than the stable form. Uranium has no stable forms. It is all radioactive. It is all emitting. U-235 and U-238 are very unstable, and they will be emitting different things from the nucleus in order to try to get rid of this excess baggage they've got in the nucleus. But it's not worth the effort with uranium because it's never going to get there. So nuclear radiation is what is actually being emitted by these unstable atoms. And so there are different things that can be emitted, and we're going to look at several of these. An alpha particle is basically a helium with 4 neutrons. Okay, so 4 neutrons and 2 protons, and so it has a mass of 4, and it has a charge of a +2. A beta particle, and these are the symbols for them here, is a 0 - 1, which means a neutron changes to a proton. I know, it's like magic, right? And then gives off an electron. So all kinds of crazy things happening in there. Beta particles do not have mass. They only have charge. A positron is a proton that changes to a neutron and emits a positron. And then finally, gamma rays have no mass, and they don't really have anything, but they do emit energy, and they do that to try to stabilize their nucleus. You can also emit a proton, or you can emit a neutron. Okay, now I told you the world of nuclear radiation is completely different from all of the other rules of chemistry, so you're just going to have to kind of buy into this and trust all these scientists that came before us, like Einstein and those guys. So the four main types of radiation that we look at are the alpha particle, the beta particle, the positron, and the gamma ray. Alpha particles are 2 protons and 2 neutrons, like we already said here, and so we write it like that. A beta particle is a very high energy electron, basically, so that's why it has the E there. A positron is, wait for it, a positive electron. I know. Gamma rays are high energy radiation that is released from the nucleus, so it really doesn't have any mass or anything. It's all about energy with a gamma ray. So just from that we just did, let's see if we can give the name and symbol for the following types so you can look at your table and come up with that. Okay, so the name and symbol for alpha radiation is, right, the helium with 4 mass and 2 atomic number. Radiation with a mass of 0, an atomic number of +1 is going to be what? Right, the positive electron, I know, which is called the positron. Radiation that represents high energy radiation released, it's only energy, so it's going to be nothing and nothing, and it's going to be what? Right, a gamma ray. That just sounds like science fiction, doesn't it? So we have to protect ourselves from radiation. I don't know if you have ever studied this at all, but there was a lady named Marie Curie, and she studied radioactivity with her husband, and they looked at this radiation. They didn't understand the problems, and so she died very young. There was another lady named Rosalind Franklin, you may have heard of. Rosalind Franklin did the work so that we could figure out what the shape of DNA is. She also did X-ray diffraction and that kind of thing. Both of those ladies gave their lives for science, basically. They died at a very young age from ovarian cancer. Now we know that we have to protect ourselves, and so we do that wherever there is a radiation symbol. You have to take precautions depending on what type it is. For an alpha particle, really just your clothes or a piece of paper is enough to shield you from the effects of that. Gloves and a lab coat will shield you from beta particles. But for gamma rays, which are more high energy, then you have to have a lead shield or thick concrete wall. And if you've ever had dental x-rays, that big heavy apron that they put on you before they do your x-rays, that's what that is. It's got a big sheet of lead in there to block that. You can also limit the amount of time you spend in the radioactive source, or you can get far enough away from the source where it doesn't bother you. So an alpha particle only can travel about an inch, 2 to 4 centimeters, where a beta particle can travel about 100 times that, and a gamma ray can travel 500 meters as opposed to centimeters, so a lot farther. Because remember, it's high energy, so it can move. Depth of tissue, this is how deeply they can penetrate. Notice gamma rays can pretty much go through you. Shielding, we said, paper and cloth for alpha, heavier clothing and gloves for betas, and then the full Monty, the lead and the thick concrete for gamma rays. Something that you may see, an alpha emitter is a radium-226, a beta is carbon-14, and technetium is 99M, and when they're a gamma emitter, you'll see that little M sign there, because that's how we tell if it changes or not. So what type of radiation would you think would be blocked by a lead shield? Now, what's the maximum that we could block with a lead shield? We can look at our table down here, and we see that lead is necessary for what? The gamma ray, that's right. And paper, however, can protect us from what? An alpha, but none of the others, right? Now, if you're behind a lead barrier, none of those are going to be able to hurt you, but the maximum is going to be that gamma ray. So that's the end of section 9.1, our introduction to radioactivity, and I'll see you soon.